talk about some acronyms today. The generalization has become a great problem these days, and as the previous speaker said, we need better architectures to start improving our coding quality, and with that improve maybe code speed, maybe power consumption. And I would like to tell you that there are other possibilities, like using the opportunities given us by the Intel CPU. We have XMM and GPR, which are extended multimedia extensions and general purpose registers. And the SSE is the Intel's name for its use of single data and single instruction and multiple data. So you can fit multiple data operations in one instruction. And I'm going to prove to you that it's possible to use general purpose registers in programming and the other way around. In short, there's going to be a little more introductory talk than examples in our general world, and then I'm going to speak about using XMM registers for general purpose computing, and introduce another old trick with the FPU, and then the other way around, simmed with GPRs, and then to conclusion. First, the computer world is getting more general these days. The technologies become standardized and more unified, and people try to make cross-compatible components to standardize pretty much everything. Why is the world getting to even higher programming languages? So we can all do programs quite easily, like the .NET and C#, which are really high languages. But assembly needs a kick in its generalization, and it comes from the simmed architecture. There have been some examples, not all are listed here. The general purpose computing on a GPU, you use graphical processing unit to calculate mathematics, not even related to 3D or even 2D. And NVIDIA has got CUDA technology and even produced Tesla servers with that, and unified shaders. There were pixel vertex geometry before, and now they're all unified with the last architecture. Actually also responded with unified shaders. Now the question is Intel making a counterexample? Because it's planning multi-core CPU in the future, where each core has its own assignment. One is for floating point, one is integer. But I think that it's even more general, because it's only a one CPU, and you can use to do many things with that, starting from integer and maybe even assignments that you can't imagine today. And now the great talk about XMM registers and how to use them for general purpose computing. The registers are named from 0 to 7. There were 8 before. Now with 64-bit architectures there are 16 of them. They're designed to do parallel operations. With floats there you could do 4 single or 2 double operations with one cycle. And you can also use integers by byte word, d word and quad word with The integers can be signed or unsigned. It's completely dependent on the programmer, and even double quad words are supported with some effort. It's not straightly supported by the architecture. And of course, Boolean doesn't care about data types, but Intel has made a small trick here. It detects the data type, and correct data type is always faster. We can also support scalar operation, which is very common to general purpose computing. You have some multiple operation, you do it with only one data unit. Some operations. We have a lot of logical operations, some shifts, and we usually use them only on XMM registers, but we can always use them on memory, and we don't even use general purpose registers for it. And here's also the point where we have multiple AND operations, but they act as the same, just we need to choose the right operation for the right data type. The less common knowledge is the huge amount of instructions you can use for general purpose, and starting from the move instructions, you can shuffle your data from general purpose registers to multimedia registers, and these move D and move Q are for double word and quad word data, and also you have move GQ, which takes memory as one operand, and you can move 60 bytes of memory to an XMM register. And this is pretty common to use a stack when you roll out of general purpose registers. But what you should do is, when you use no SIMD operation in your program, you can not push registers but move them to multimedia registers, and when you need it, you can fetch it back really quickly. Push operation needs memory has latency, all sorts of problems, but moving through, taking your EAX register and moving to XMM0 or whatever, you have 16 of them on current architecture, you can do it really quickly, and you have efficiently 32 registers, and even half of them are empty, because even the 64-bit general purpose register takes to space the half amount of a multimedia register. But what we do here is we're using SSE in a way it wasn't meant to be used, but through this we can use it more effectively. Here's one example: move Q, XMM0, RAX. It only fills the lower part of it, but you can always shift it to higher part and move another value to its lower part, so you can effectively double the amount of data you can save in multimedia registers. Of course, there come some problems. The length of the instructions, which is 5 bytes, and half a clock throughput and a 2 clock latency. When we compare it to a regular move from RAX register to any other 64-bit register, it's only 3 bytes and a third of a clock. These measurements are all done on our last core 2 architectures.
There is one question from Sleep.
Okay.
If we start using XMM as general purpose registers, then what is the purpose of general purpose registers? Also in parentheses, like when to use them, when to use general purpose registers and when to use XMM registers.
The last point I made was, if you need more memory, the XMM registers are free in your program when you don't do any multimedia programming, or you don't need packed data types. You can use it as a spare memory. Very fast spare memory. It's like it's even better than L1 cache, because L1 cache has at least 3 clocks of latency, and you can use it as a memory, and you can do operations on it. Like when you push your value to memory, you can do only limited operations on it. But when you move your value to MMX register or XMM register, you can do all sorts of stuff. Like I mentioned, the logical operations, which are common to GPRs, and there are also multiple and divide operations. I hope I answered his question.
Well, yes, another thing to add is you can't do indirection with the multimedia registers. You will also do that general purpose registers.
Yeah. There is also the push pop example where this is a situation where we will win. If we compare it to a regular move to another 64-bit register, we lose because the XMM latency is a bit more than shuffling through registers, the RAX and others. But moving back from the multimeter registers to a 64-bit register is faster with only 1/3 of clock of throughput. Some more examples. After you do your move Q, you have your general purpose register in multimeter register, and you can do a shuffle operation. We have a byte swap operation with Intel architecture which swaps the order of bytes in your machine word. Is it 32-bit, 64, or 16-bit, whatever. And with the shuffle operation, you can not only change the order, but you can put them in any order or broadcast 1 byte to any bytes, and you have 2 times the memory the 64-bit data type usually has. So there are a lot of advantages, but like with the last example, a lot of memory usage. You need to have 60-byte memory region where you hold the shuffle algorithm, how to shuffle it, and you need 10 bytes for the instruction itself. But if you don't care about the memory, because memory is free today, then it's nothing to worry about. Only a little more clocks. There's 8 versus 6 clocks with the byte swap. But if you do a lot of these, then the latencies will hide, and you will get the efficiency about 6.5 clocks per byte swap. So it might be convenient to use multimedia registers sometimes. And there's a scenario brought up when you need to byte swap and copy the swapped bytes. You need to add some other shuffling on it, and you need to preserve the value. Then the XMM register is 2 times longer, and you can have the spare result for any later usage. You can shuffle it again and then fetch the other value you preserved. With byte swap, you need to make a move to another register which uses another register, and you might run out of memory if you're unlucky. Other examples are data movement, arithmetic operations, and even comparison, which is fully integrated in the SSE instruction set, and bit wizardry and logic. I hope many of you remember the FPU was used to move data some time ago. They used successive load and store operations to move 8 bytes at once. With 32-bit architecture, you will take only 4 bytes at a time. And if you start to unroll the loop, you run out of register pretty fast. You have only 8 of them, but you can use 6, I think, at maximum. You have got plenty of floating point registers. They still remain 8 even on 64-bit architecture. But there's another problem with 64-bit architecture. You don't need these floats and stores anymore, because 64-bit extensions have already the same amount of bytes you can move, and you will lose the edge with your floating point movement. And even better, you can take the SSE and move double the amount. It's 16 bytes then. And with the 64-bit architecture, you have 16 of them, so we have effectively moved to 256 bytes in one pass of a loop.
Also, weren't there some potential problems with the floating point move? I think you had to make sure the FPU control flags was set correctly, so you can throw exceptions on some.
And the bits won't change. Rounding errors.
If I recall correctly, changing the FPU controller was relatively expensive.
Rather slow, yeah. And another problem is that when you load something in the floating point unit, it's a philo architecture, so you push it like on a stack, and you can only get the last one, not the other order, and the shuffling them again takes time, and so that's slower. I made some tests. I hope you can see the results. I started with a simple move instruction that is really a macro instruction from ESI register to EDI, or depending on the code you're writing, maybe 64-bit. Yeah, should be on the other side. It took 640 clock on a move instruction, but it took 2000 clocks on a regular move through EAX register. And this is where I did some unrolling. And we can see that the best way to go is replicating the move instructions with dword, and you can get the best clocks out of a loop. Even unrolling the move instructions didn't help. And then I tried move D with XMM, and it was still slow. Now with 64-bit architecture, you have 8 bytes at a time, and it's a bit faster, but the bottleneck is somewhere else, because it should have gone twice the speed. And the only thing I could do was unwrap the move apps. This is aligned, packed the movement, and with 8 times unrolling, I could get the best speed out of it. So the floating point is somewhere here with 562 clocks. I should mention the data moved was the same all the time. I can't remember anymore. Was it 2 kilobytes or something? So these are comparable values. I didn't take into account the latency, so there might be some errors in here. And as you can see, the too much unrolling can hurt the performance. So 2 times unrolling is some 500 clocks, and it climbs to 700 here.
Sorry.
Yes.
Next question from M. Hajduk. I don't know how you pronounce it. In which program Madis measured number of clocks of these algorithms? He asks how you measured it.
I just ran it some 20 times and took the average.
Read timestamp counter?
With timestamp counter, yes.
Okay.
So actually the 2 decimal places behind it are actually relevant, because the timestamp counter is some inaccuracy of 40 clock cycles or something.
Also, you should do the timing on an AMD processor as well. I believe that Intel has some special short circuit hardware for the improved repeat move stream.
Sorry, I should have mentioned it. It's done on a Core 2. The numbers are totally different than others, but usually any Intel 64-bit will have the same results with XMM registers. And what's the crucial part of this slide is that the best you can get is 285 clocks compared to the best with the most common instruction sets. You can get almost twice as fast, or even faster. But again, it hurt the performance when I unrolled too much. I'll give the algorithms to anyone who are interested later.
Madis, did you have a chance to check what happens if you exceed the number of moves compared with your cache? What happens when the cache capacity?
Okay, I didn't try that because the data set was only like a few kilobytes, but the L2 cache is like 2 megabytes on a core 2.
So the problem there is that
the next bottleneck is memory.
yeah, but I'm not sure you may have different bottlenecks going to the FPU from cache than you would going to the MMX.
Yeah, that may well be, but that's only a preliminary test, so it needs a bit more testing to be absolutely sure. But
I would just sound a note of caution that
yeah,
it would be, I think, useful in making the comparison between, you want to compare how the floating point and how the special registers work rather than testing how Intel's microarchitecture works. In other words,
it works.
you ought to have a
yeah.
data size sufficiently large to exceed the size of your cache.
It would be better to do it on a larger data set, but with this small amount, like 2 kilobytes of data, I'm going to more like general programming where you don't need a megabyte of data to be transferred, but more like a few kilobytes, and which is the best way to go when you need only a few data transferred. So is it better to take a floating point unit and move the data quickly, or is it better to take a multimedia extension? If we go higher, then there are absolutely different algorithms, not even those simple move apps, but we need to tell the cache what we're doing, and this was a too simple test to give the right results at those high level of data movements.
Yeah, because if you're going to move a lot of data around, you can use the write-through instructions that don't pollute the cache. That can be pretty important.
Move NGPS and NGPI and others, yeah. Now the other way around, seemed with GPRs, the generalization works both ways. There was a question before about this, when to use what. If you really want, you can use general purpose registers to make packed instructions. We have first here copy an important byte, word or whatever to the full register, and multiply is the best way to go then. You take a constant in a repetitive pattern like 01, 01, 01 in hex, and you have copied the first byte in your register to all the bytes in the register. Or you can do the same with the other constants where the pattern is longer and the 1 represents the start of each data set. And with 64 bits you can easily fill 16 bytes of interesting data with one multiplying instruction, and multiply somewhere about 3 flops plus some latency on a core 2 architecture. Simmed addition and subtraction is also possible, but it's a bit tricky because you have to use double-sized constants, and when you add a byte to another byte, you can only read a byte afterwards, and you have trash in the higher byte, and you need to interleave them, so you have word alignment, but you add bytes. So there's a bit trashing, so it's not very efficient, but I think there might be use somewhere where you don't have XMM and you definitely need some multiple data to be squeezed through single instructions. Even trickier are multiplies, because multiplies are only possible with one value. There's an example with, we have a byte here in the EAX and multiply with this kind of pattern, and we have interesting bytes in here. We can do other patterns and have these kind of values here broadcasted everywhere. With multiply, you can only say that I want these values to be multiplied by 4, and you have these values multiplied in the result. But if you need to have different constants multiplied here, it's rather tricky or even impossible with the general purpose registers. So better get yourself an XMM then, or try to find another way to do it. But multiply is also possible. So, coming to a conclusion finally. The generalization between the multimedia registers and general purpose registers is possible, as we've seen, with some tricks involved. But with some thinking, it might be even more efficient than the conventional methods of using general purpose registers. Of course, it all depends on the application and on the programmer, but in theory it's possible, and I'll put some examples together where it really works. And while the whole world is moving, why should assembly stand still? Because other world is generalizing, and I couldn't see the same kind of behavior in assembly. We have too many instructions and not much to do with them. Thank you. If you have any more questions, I'd like to answer.
Okay, no questions. Looks like no questions. We should wait for a few seconds until the video catches on.
Okay.
For them, but I think no questions. There is some discussion about it. Okay, I think we can move on.